Hello.
Including quantum machine language. And with these few words, I'd like to welcome him and request him to give his talk on quantum
information. Hello. So thank you, Bhanu, very much for your introduction. And thanks for this opportunity to speak. Right. So I will speak about, how to use systems which are not so well under control. So by quantum computing, we generally mean creating a highly controlled system where you have a collection of qubits and you can control each at your will, and you can do gates between any pair of them, which is a very, very important challenge, but it's also a very difficult challenge. So I would be, one of my motivations is to look at systems where we are not controlling so much. Say for example, let the interactions in the system be frozen. And when interactions is frozen, then if you take the simplest ingredients, say build it up with qubits, that is a spin chain. So I will look at a spin chain for a large part of my talk. Okay, and the talk will go in two ways. So I will look at what I was saying, how spin chains can be used for quantum information applications. Of course, there are many activities in this area, right? So my activity is only one type of thing here. So typically I consider cases where we do quenches or fast protocols in spin chains. So non-equilibrium dynamics of a closed system, unitary evolution, that kind of thing. And then some ways in which a spin chain can help us there. So I will go through simple examples such as, how it can be used as a quantum channel to connect quantum registers, how it can be a source of entanglement, make maybe quantum gates, and perhaps even some algorithms. Of course, it is very difficult to make it work as a universal quantum computer because of this constraint that I said, that couplings are fixed. Okay? Of course, there are many other approaches to using many-body systems, which I will not go to. So I will not go in the area of things like adiabatic quantum computation or quantum annealing or even topological quantum computation. So these are other kinds of activities. Okay? Now, of course, one can think also of the reverse. Okay, the reverse is more a theoretical side of things, where we would like to apply various quantum, various measures which have, which arise in the field of quantum information, and apply them to spin chains. Okay, and this per se has just the motivation of understanding the nature of correlations which are there in the system. Okay, so in a quantified way. Okay, so it's very difficult to put precisely, but when you examples, I will point out, potential applications. I mean, a minimum application could again be that, once you understand how entanglement is distributed in a system, you can probably use it for, say, like an entanglement source. But another thing is, even for understanding, if you are to write an approximate description of some parts of a system, if you understand the entanglement structure, it may help you to write an easier, variational wave function. Now, right. So as I said in the start, I put many-body spin systems in my title. Sometimes I put spin chain, but what I mean here is a slightly broader concept. Okay. So we will use the term loosely. So we have a set of quantum spins. So actually, in all cases, I will be using exactly qubits, so spin half systems. Yeah, so they are fixed, and the couplings between them are also fixed. Okay, and though I use the word chain, they can have potentially, I'm allowing also for, longer range couplings, perhaps decreasing with distance. Okay, so not just nearest neighbor. So in general, I'll be using in the end in a much broader sense, where there could be any sets of frozen couplings. Okay, in some examples at least. Yeah. And there is an important point. Okay, of course, nature gives us lots of spin chains. Yes, so lots of compounds and things would actually. So any lot of natural magnets. Okay. Though originally when I did my work, there was some motivation to use. So that was long before we were having so many designer systems for quantum computing. But these days I refer to the main scenario of my application is for the quantum simulators. So analog quantum simulators in particular, where you make systems which are many body systems with permanent couplings in some a Josephson junction array or an ultra cold atom lattice or a quantum dot array, and you try to find out some application of those, okay, without controlling too much the individual couplings. Yeah, in some examples I'll be using periodic, but for my primary application, I will be using an open-ended because I'm using it to transfer information from one place to another. But in some cases I'll be using, yeah. It's sitting on a lattice at the moment. Yeah, so not itinerant particles, no. Okay, so now let me go to the more clearer description of what I was meaning. So when we are, as we are building up quantum computers, we face with a basic obstacle. Okay, so quantum computer, each say register, okay, is made of some qubits shown here, and sometimes we just use the interactions which are naturally there between qubits, but these we know decay with distance. Okay? So essentially, qubits interact with each other through, fundamentally through what we call off-shell interactions. Yeah, so through which kind of through the electromagnetic field primarily and not primarily, entirely in this case, and falls off with distance. So there's a problem of doing more longer distance gates, obviously. Okay? So after some distance, it's a problem. Okay. So sometimes people also use a common bus mode, okay, to couple them. Okay? But generally, there is a limitation in the size of individual registers. So you will sooner or later want to connect different registers up through, through these green lines shown here, which are the, how these registers are, talking to each other. And what you need to send between them are quantum bits or entanglement. So unless you send a qubit from one place to another or establish a good entanglement between one qubit in this register and another qubit in that register, you do not really establish a connection between quantum computers. Okay? So if you have established, say, a perfect entangled state between one qubit in this bottom register and one qubit in this top register, for example, then you can teleport a qubit from this register to another and do some gate in this register and then use another entangled pair to teleport it back, for example. So this is how we can do gates between distant registers, and they start working as one quantum computer. So to make different registers work as one quantum computer, you would need to exchange qubits and entanglement. Now, the usual scenario suggested for these is to actually use photons. Yeah, but this is just a toy example, need not be 8-bit register, could be larger ones, okay? Because people are able to construct much larger registers these days, okay? But still this kind of limit is fundamentally there because either you use a common bus, in which case the bus becomes more and more sluggish as you put more and more qubits, for example, in ion traps, or you use just the nearest neighbor registers, such as in a quantum dot array or that where you again you're, I mean, right. Oh no, this is my no. Don't read anything into it. No, this is just my drawing. Yeah. It's not deliberate. No. Now we use photons to usual idea is to use photons to connect them. So you transfer the information in a solid state qubit to a photonic qubit. The photon goes there and maps to the other qubit, okay? Or some electromagnetic waveguide, or you may actually create entanglement between qubits and photons and do some kind of joint measurement to establish entanglement. So there are various scenarios like that. Okay? There are also scenarios where you actually try to move a qubit from one place to another. Coupling. Okay. However, what I would like to suggest is that one can also use something like a chain of spins. Okay, so you see there is this spin chain with all these frozen interactions. Of course, frozen interaction means an excitation anywhere in the spin chain can move both left and right. Okay, but they can move left and right in superposition. So they will always do a quantum walk and say you have an excitation in one end that could transfer to the other excitation, of course, with dispersion and everything. But this is a way you could actually transfer a qubit from one quantum register to another without actually interfacing between different types of systems. So the idea is not to really use hybrid systems, but use solid state qubits of the same type, one a more controlled region, which is a quantum register, and a less controlled region, which is the bus. Okay? But less control means here you are not individually controlling couplings to swap information from one to another, but the information is flowing naturally due to the, say, the dynamics of the magnons or spinons or whatever is there in the system. And this is a better picture for that, showing why even, so is that a problem, this signing out and stuff? Or okay, yeah. I say okay here, yeah. Oh, so anyway. So I don't know. So I don't know whether people in Zoom can see this. Hopefully not. But this is in a very bad place. Should I leave? He's not leaving this thing in the. Yeah. Ah, right. Yeah. It is possible that people in Zoom can actually still see my slide. So I will keep on speaking just to save time. That so what is being shown is that there are two. So even when you can control qubits, the main problem happens is that you come with your probes from a macroscopic world, right? So there are big knobs which you control, then you make thinner and thinner and thinner wires, and you hone into your individual qubits. But there will come a time you cannot pack more controls into the region. They will have some highly controlled regions which have to be separated by less controlled regions. Now, you cannot completely get rid of the coupling in those less controlled regions because then you will lose all connection. So when you have frozen coupling regions which are not being controlled, like a line of qubits with frozen interactions, that is a spin chain. These are the types of spin chains I'll mainly be talking about, not necessarily the natural spin chains in nature, where even controlling an individual spin is very difficult, right? So, but quantum simulators where the couplings are frozen, so the information can flow. And I'm just awaiting some password entry here. Which meeting they're talking about? What if you just close the corner? Is that a problem? Okay, I think this is all right now. Yeah, thanks. Okay, so I've already spoken about this slide. I think the people in the room had probably more problem here. And right. So this is the first schematic I will consider. So consider a spin chain initially in, say it's a ferromagnet. So we have prepared an initial state with all spins aligned. And in one end, we have put a qubit in an unknown state. Okay? So alpha up plus beta down. Okay. And then they are coupled by the isotropic Heisenberg Hamiltonian. So XX plus YY plus ZZ, okay, equal interactions. And I also assume that they are uniform nearest neighbor. And then we want to see how this information flows from the left end to the right end. So this is very, simple dynamics to calculate because, of course, as I said, we have with cos theta by 2, we have the zero state, the down state, which is actually an eigenstate. So it has no evolution, okay, of the ferromagnetic coupling. Okay. And then we have a single flip, which is like an excitation, which is like a quantum walker. So at every step, it goes in a superposition left and right, disperses and reaches the other end. Okay. So all we are trying to optimize is the transfer of this excitation. So this localized magnon. Okay, so it's a combination of all possible, magnon eigenstates with, one flip. Okay, and we want to see its amplitude to go from first side to the capital Nth side. Okay, so everything depends just on this amplitude of transmission. And these are some of the results. Okay, this dynamics is very easy to do. Okay, because it's a single excitation sector, it's open-ended chain, so everything are just, the eigenstates are just the cosine transforms. Yeah? For a ring, they are the Fourier transforms. For an open-ended chain, they are cosine transforms. And so you can draw a graph for different lengths of chains, and you see there are some interesting things here, like, right. Okay, so fidelity here means that, say you take any initial state that you want to send, yeah, sine theta by 2, 0 plus sine theta by 2, 1 to the power I phi, any arbitrary qubit state, and then you find the final state which has gone to the other end, which will generally be a mixed state because it will be entangled with the rest of the thing. So you take the overlap of that mixed state with the initial state that you want to send. Exact, then its fidelity is 1. Yeah, but if they are slightly mismatched, the according to the Born rule, the fidelity will not be perfect. But then you average over all the possible initial states you wanted to send. So sending means not just sending the ratio of 0 and 1, cos theta and sine theta by 2, but also the I phi, the phase, relative phase. So yeah, so and then you average over the whole, all possible qubits. So that is called fidelity. And that thing is known that classically best possible is 2 by 3. This is a fundamental, result in quantum information long time ago, that if you just measure a qubit here, say you use the Z basis to measure a qubit, okay, and then you just call up your friend and tell, I have got these results, this is my statistics of my results, then he or she can reconstruct the state at best with 2 by 3 fidelity. This average fidelity cannot exceed 2 by 3. So if average fidelity exceeds 2 by 3 means that actual quantum state must have been transmitted, because just by classical messages, you cannot get above 2 by 3. So we can use it as a benchmark, as a threshold, that if you are doing better than that, which kind of one can do with up to, say, 80 spins or something, waiting a very long time. This is a dynamics. We wait for a long time, and exactly at the time at which the highest fidelity is reached, to reach at the other end, we stop the dynamics. This is why I'm talking, these are all quench protocols. Suddenly start the interactions, suddenly stop the interactions after some time. Okay? So we have to have that much ability to stop or start the interaction, or stop or start the interaction with the end qubits. Okay, but we don't require control elsewhere. Now, another interesting thing is this black line is the entanglement that can be sent from one end to another. How is entanglement sent? It is sent in the following way. Hopefully, I don't have any graph. So you can actually entangle two systems and send only one part through the channel. And that actually goes for any length. Okay, the amount of entanglement which reaches is 1 by cube root of n. It is related to the first peak of the Bessel function, which reaches is 1 by cube root of n. So you can always, for any length, you can send entanglement, means for any length, it is actually a bona fide quantum channel. But now the question arises, so in quantum information, we kind of want perfect communication. This is one of the constraints. We do not want this less fidelity communication. You see, you saw my fidelity was going down. Okay, when we want to transfer things, we want the best possible, transfers. And how do we achieve that? Okay, so one thing is what strategy people generally try to use. People generally try to use off-resonant interactions. People try to use what we would call super exchange between very distant things by some kind of intermediary. They might as well use a spin chain for that, okay? But that is a very slow, very long time thing, okay, a super exchange. So a lot of decoherence will happen by that time, okay? What I am using are really what is called on-shell objects. So I'm using real particles going from one place to another, okay? So real magnons going, no, not a virtual interaction through virtual intermediaries, okay? I mean, real particles I'm using. So it is much faster, but the price you pay is that they have dispersion. So they will, you will not get a perfect thing. So that can be cured with a very simple kind of encode, which converts this imperfect, fidelity of transfer to a probability of success. When you are successful, then you get perfect state transfer. So what you do is, say, this is your arbitrary state, alpha 0 plus beta 1. Then you do a quantum and you encode it in a dual rail, okay? So first you encode just in 1 qubit and then do a kind of C0 operation, okay? It's not exactly C0. There will be some particular gates here, which would convert the state to up, down plus down, up with alpha and beta, just the interaction of the initial qubits to start with, okay? Then they flow through the chain, and at the end, you check whether an excitation has arrived or not. Yeah. Yeah. No, it's now for the 2 qubits together. So initially it was in 1 qubit, and then we did a quantum gate between the first qubits in each chain, which delocalizes this information. So it encodes the information in up, down, and down, up. Okay. What is the advantage of that is at the receiving end, I can check whether one red ball is there, whether an excitation is there or not. That does not destroy this information there. You see, there may be some phase information not be destroyed, okay? So that will still be there, and then you can use the same local gate to and kind of bring back it to 1 qubit. Okay, so this is a heralded thing. So you will, if you do not find an excitation in this in the receiving end, it has lingered somewhere in the chain, right? So you will know that you have not been successful with that probability. But when you are successful, you have the perfect state. Okay, so it's a heralded scheme, and this is how imperfect fidelity converted probabilities of success with perfect fidelities. So then we go to this. So we now become a slightly more ambitious. Okay, so we were so far talking about just transferring states, but suppose you want to even reduce this dispersion. Okay? This can be done with some engineering. In fact, naturally the harmonic oscillator and on a particle in a square well do these. Okay, this is called mirror inversion. So if you start with any localized wave packet in a square well, after some time you'll see it has gone to its opposite shape. Okay, this requires just 2 ingredients. It requires an integer spectrum. Okay, in case of square well, it is k square. For harmonic oscillator, it is k. Both suffice. Okay, and it requires successive states of opposite parity, okay, which always happens when you have confined system. Okay, so once these 2 conditions are fulfilled, it is very easy to prove that a wave function evolving in time will have complete mirror inversion. Okay. Now, on top of this, we use one can use a XY chain. Okay, when you use a XY chain, so I'll come shortly to that. that can be mapped to non-interacting fermions. Okay, so XY chain means XX plus YY, nearest neighbor interaction. So there's no ZZ. This can be mapped to free fermions not seeing each other and just hopping along, so that the dynamics of one is replicated by the dynamics of everyone. Okay, so then you can really have a spin chain in an arbitrary excitation sector which fully mirror inverts. Okay. So these are beautiful dynamics to implement if, and for a spin chain, you can do that if you engineer the couplings in a particular way, okay, to get this integer. So these couplings are engineered in a, did I miss a slide or something? Yes, so, okay. So let me show this. This is shown as a problem here. So suppose one wants to, so we want to use this event to do gates, okay, quantum gates. What will we do? So consider this situation that I told that these things map onto many free fermions who do not see each other. Okay? The XY spin chain. Okay. Of course, fermions do not see each other except the fact that when they cross each other, they have to get this minus sign. Okay? And can we use that sign itself to do a quantum gate between distant qubits? Okay. And particularly the architecture we will consider is many qubits like this, okay? But we want a gate suddenly between this, the two qubits, say, connected with this red double arrow, okay? How are we going to achieve this? They're very far, they are not naturally interacting. So our plan is the following, okay? So consider these as set of distinct atoms held in tweezers or on top of, I'll show a picture soon. Atoms helps in individual micro traps. And then you have an ultra cold atom, say optical lattice on top of it. Okay? And in that optical lattice, you synthesize these XY interactions. When you synthesize them, then there is this mapping between qubits. Okay, individual qubits are shown by these sigmas to fermions. In 1D, fermions are very easy to synthesize. It's known historically from a long time ago, highly used in condensed matter, that you can create, you can map to free fermions. Okay. Now these fermions, what will happen is, so let me skip one more. Okay. What will happen? So this is the XY interaction. As I said, they are exactly identical to these free fermions. So they will not see each other, but when they pass each other, they will get this -1 sign. And how will that help us in the gate is as follows. So this is the easiest example to look at. Look at a quantum register of these 6 qubits. Okay, so with the last 2 qubits, we want to have a quantum gate. Okay, now what do we mean by we want to have a quantum gate? We want to have a quantum gate which entangles them. Okay, so this is called a maximally entangling gate. So it could be a control Z gate or a control NOT gate or any gate which creates a maximal entanglement. That's what our aim is. Okay. So we synthesize this XY model in this array of 6 qubits and consider these states with the the ending qubits being 0, 0, 0, 1, 1, 0, and 1, 1. 4 things. Okay. So only the 1, 1 thing actually has 2 fermions. Okay. So the mirror inversion dynamics, when it happens, okay, that exchanges the fermions. Neither of the first 3 will have any sign. Okay, so they will go like that. They will still exchange. 0, 1 will go to 1, 0, so it's off diagonal. But the 1, 1, this is the basis of the gate. 0, 0, 0, 1, 1, 0, and 1, 1, right? Only the 1, 1 will get this -1 sign. Right? So this is a very easy way to do the quantum gate, okay, between two qubits at the ends. Okay, so we have shown one more step of improvement. Just rather than just communication, we can also use to do a quantum gate between them. Now, we could, so this is the same. So now how it will be done in practice in such a system, you can, for example, take atoms trapped in individual tweezers, or here, I think we put them at the end of optical fibers. They are being balanced, yeah. And there's this optical lattice connecting them between the end. Okay, so here the connections are frozen, so we can't synthesize the ones in the optical lattice. And then we push with the force of the fiber, we push the atoms closer to the lattice so that you set up a exchange interaction, okay? And then you can set up the XY model. For XY model, you require a little bit of trick. I will not go into that. Naturally, it is isotropic Heisenberg, but you can do some stuff there, okay, to get XY. And also you have to put some kind of walls of light, okay, so that you cut off the spin chain elsewhere. And then you can connect any to any. So you succeed in this kind of trick to do this any to any connection between many atoms held in tweezers. Now, of course, these days, distant atoms interact naturally by these Rydberg interactions, very long distance. But you might still want to use something like this in addition to have a stronger interaction at some distances. If you want to have varieties of interaction strengths, for example, then these kind of things. Now, let us consider this. This is the kind of engineering one needs. Each of these couplings, J1, J2, J3 in a spin chain. No. Yeah. Exactly. Right. Exactly. So I'm not considering Rydberg. What I'm telling you, these days one can do Rydberg things where there is a long range naturally. Yeah. When I wrote this paper, people had only seriously considering on-site interactions for ultra cold atoms in optical lattices. So when they hop on the same side, they have a collisional interaction, and the different side they don't have, right? So the long range was even more important. Okay? But what I'm telling is, in these days, with the advent of more distant interactions anyway, but suppose you don't want exactly the natural interactions, you want some kind of other mechanism and some other strength, then one can use those kind of thing. Now, this is still in the context of, so in fact, there is no implementation I'm talking at the moment. I'm talking when I show this picture, is that we require in any system, if you can synthesize this kind of interactions, the square root of small n and capital N minus small n, okay, it's very tough to synthesize, of course. It's a mathematician's thing that this write down the nearest neighbor exchange interactions to be like this, whereby exchange has to be taken with a grain of salt. This exchange is XX plus YY only. So it's not isotropic exchange. The ZZ has to be got rid of in some way. Okay? Maybe by frequently flipping alternate spins, and they get rid of the Z. Okay, and then if you manage this kind of interaction, then a lot of wonderful things happen. Okay, you start with this nil state. Okay, up down up down up down at a certain time t equal to 0. This has no entanglement. Right? Then at time t star by 2, what will happen is you will have many perfectly entangled Bell pairs between diametrically opposite spins. Okay, and it is completely easy to prove from this free fermion picture. It is not that there is an effective super exchange between those pairs. That's not at all the case. The fermions are really going through the chain, so nothing is virtual. So people are crossing each other, but T star is a time which is proportional to the n. Okay, I have forgotten the exact time. I should have written in the slide. It depends on the interaction strength J and the number of spins. Okay, but it is hopefully it will be there in some slide or other. But yeah, it's a time linear in the number of spins. No. So I'm assuming really the coherence time is much larger than the system. Yeah, so it is not related to T2 star. Yeah, this is star is used unfortunately here. I would say theorists use T star. Theorists don't know T2 star or not have T2 star in mind. T2 star is infinite in this this presentation, but of course one has to make the whole dynamics complete before the coherence time. Okay? Now, but in half a time you have those Bell pairs. Then after half a time you again have this disentanglement. So this is if you can synthesize these magical couplings, and then again it oscillates. Okay, so the entropy goes like that. Okay, So we say we have entropy dynamics from area law. In this case, area law is 0 in this case. We have a nil state, so no entanglement. Area law to volume law entanglement. The volume law entanglements are very of interest to people. However, here we have volume law entanglement in a free system, not really due to the ergodicity of the interactions. It's really the free movement, free quasi-particles. Now we try to get more ambitious. Okay, we want to go say 3 particle gates with connected spins, and some important gates are this Toffoli and Fredkin. Okay, Toffoli has an interesting thing. It is the fundamental gate for these are fundamental gates for reversible dissipation-less classical computing, which was very popular in the late 80s, and then it went out of favor because, of course, very difficult to do dissipation less. Okay? But for quantum computing, we have progressed one more step further. Okay, so we don't even think of T1, we think of T2 star, right? So we have gone far beyond T1. So it makes sense to think about, indeed about reversible computing once more. But anyway, this control not Toffoli is one of the basic gates for it. And also, it is a basic gate for quantum computing. So with the Toffoli, if you just add the Hadamard is the one which does the basis change between 0 and plus minus 0, 1. Just those 2 ingredients make complete quantum computing. So how to do those gates easily is an important task, okay? Or can you do it with less control, okay? Naturally, if you wanted to have one Hamiltonian which you switch on, this you just take logarithm of the unitary, okay? U is e to the power IHT, you just take logarithm of u. Of course, it's not unique. You can take logarithm in many ways. You get 3 body interactions very naturally because it's a 3-qubit gate. So can you do it with just 2 body interactions? So this is where we applied a little bit of machine learning. So we had a general network of qubits. So now you see I'm seriously deviating from spin chains. Okay, so I'm just using arbitrary networks of spins. And supposedly, if you can optimize couplings in some way, okay. And then this is the architecture we found, okay. This is the one we could solve. Slide size. Okay. This is because slides are from different talks put together and. Yeah, no. Sorry. Yeah. So different students presented these things in different ways. So what we found is that you have to have z interactions between qubits, and then one XX interaction between 2 ancillary qubits, and then this is a fixed time independent Hamiltonian. Then e to the power minus IHT of that would perfectly make a Toffoli gate between the control and 2 targets. And at the end of the gate, the ancilla qubit in the middle would become disentangled again. In the start, it is disentangled. In the end, it's disentangled again. This is, of course, the bad thing about it. These couplings need to be some peculiar amounts. Okay, so it's an open problem to see whether one can achieve something close to it for, say, Josephson junction, networks and stuff. Okay, so we are still working on that, and it's not. Yeah, fixed. Yeah, so they are. I don't even can immediately answer to you how robust they are. They have some tolerance, obviously, not instantly go away, but the fidelity decreases quite rapidly. So one could even set that as a target of the machine learning, how robust it is. We just set the fidelity as the cost, how best you can realize the gate fidelity as the cost. So if you also additionally add robustness as a cost, you may get different numbers. The things still to be done there, but we have some network which does, is a frozen network of 4 qubits, which will do a Toffoli gate between 3 of the qubits, and the third one will become decoupled. Both initially, decouple means disentangle both initially and finally. And the general, scheme of a quantum computer like this would be like you will have a quantum register like a memory with many individual qubits, and then you will put them into a quantum bus, which will take them into like one gate network or another gate network. And universal quantum computing can be done if you have two, gate networks which do very non-commuting, made of very non-commuting operators. Okay, so this is very similar to the von Neumann architecture in some way. You take to this chip or to this chip according to your program, A, B, A, B, A, B, and that should be able to do any quantum computation like this. Okay? Now, one thing is how we can do some kind of perhaps a spatial search using such permanently coupled qubits. Okay, it is known. So this is just nothing but a recast of what is called Grover's algorithm. Okay, search algorithm can be recast in terms of what is called quantum walk. Okay, so and applied in a context of spatial sites. So say you have few spatial sites. So now each qubit there is, we are not using them in the full qubit subspace, but each qubit can be, so only one of these qubits at a time. We are considering this as sites of a walk. So they are empty or filled with a particle. When they're empty, the qubit is say down 0. When they're filled, then the qubit is up. Okay. So we know that if you mark one of these sites with a different energy, such as W, and you start with the equal superposition of the walker being in all sites, then natural dynamics is going to take all the excitation there, okay, in a root n time. Okay, this is nothing, just a rewording of the Grover's algorithm in terms of a continuous walk. Okay? This is very well known. Okay, but what you need is not a lattice here. For this, what you need is a fully connected graph. Okay, so we are, and for the lattice, actually, the advantage goes away. So this is the algorithm. It's by long time ago by Childs and other people, that you have marked site, just a site with different energy. You don't know where it is. So you have many places, you have a hole in one place. You don't know where the manhole is. Okay, so classically, a walker would have to really look at each place or half the number of places. Yeah, quantum random walk. Classically, you don't know where to look, but quantum mechanically, you start with all the sites in equal superposition, and you will see gradually the dynamics will bring it all there. Okay? This happens because you can just consider it as a two subspace, the rest and the marked, and the entire dynamics is just a rotation of like a rotation of a single qubit. Okay, and it happens in square root of the number of sites. Okay, so this is basically Grover's algorithm. Yeah. However, it requires every site to be if the walker is in one site, it requires it to walk to all the other sites with the same amplitude. Okay? So means completely connected graph, so all to all connection. Okay, which is of course very difficult in practice. Okay? So what we looked at is what happens when you have some interactions falling off with distance. Okay, with some coefficient alpha. Okay, so for example, in ion traps, one knows that alpha can go from 1 to 3, yeah, according to how collectively or how flatly you put a potential in the axial direction. Okay, so if they're very tight, then you go to low values of alpha, like near to 1 or to 0. I think you can closely approach 0 also, all to all connection. Okay, or you can go up to 3 when you make the thing quite flat. Okay. So, and what you do is you can actually implement this XY interaction very easily in ion traps. This is done by what we call the Sorensen-Molmar, interaction. Okay, so it's a off-resonant interaction between two qubits through the ion trap bus. Okay, and between many to many you can make with the GIJs falling off with distance. And here, for simplicity of mathematics, we considered a ring. Okay, so this is one case where we did consider rings. Unfortunately, the maths is easier to do. Okay. Now, this is the situation. And then we wanted to see when does this advantage of root n goes away. So obviously, when R is 0, means in infinitely long range connectivity, we know we have this root n. Okay? Now you increase your alpha, make it increasingly shorter range. We know the nearest neighbor lattice does not give the root n speed up. So we investigated when you have the root n speed up. And it is again using a spin chain, but not in the fully excited sector. It is using it in the single excitation sector, like many of the cases before. The maths is very easy to do because of the ring, the eigenstates are now really Fourier transforms, and then you essentially require Fourier sums of strange things to the power 1 by j to the power alpha. And these have somehow have been worked out before. These have strange names, Lark polynomials, polylogarithm, but whatever. So you can really do the things analytically. And then this is what we find, that the fidelity of really being able to do the search in this root n time falls off, and at alpha equal to 1.5, it goes to 0. Okay. So before this 1.5, at alpha equal to 10 into infinity, we know it doesn't work. Alpha, we didn't go from the 0 to 1 regime. It's a bit difficult there, okay? Alpha equal to 0 is infinite. So spin chains falling faster are no good. So how much time do I have, Banu? Yeah. Okay, no, so I'm going to the next kind of the opposite topic now. So far I was looking at how spin chains can be useful for quantum information gates. Now I'm trying to look at how quantum information measures can be useful for whether they can be useful for spin chains. I think the verdict is still out, but what we do is we kind of compute various measures to see how they behave in various many-body systems. And perhaps an experimentalist can even measure them, okay? So this measures new attributes of the systems, new entangled attributes of the systems, but does not, we don't yet know how useful that is, okay? But anyway, so various kinds of measures of entanglement have been computed in many-body systems. So Bill Wouters came out with the measure of entanglement of 2 qubits called concurrence in late 90s, okay? You know, the usual measure which people had for a long time is called von Neumann entropy. That applies only to blocks of a pure state. Okay? If you take 2 individual spins with an environment, they will be in a mixed state, and that entanglement can also be computed, okay, in very tricky ways. One measure of that is negativity, and this is where we worked a lot. I'll show some of the things. So it measures the entanglement between 2 blocks, non-complementary blocks of a many-body system, a computable measure. In the end, we will do. Yeah, no, now it is, so I've not specified the Hamiltonian at all. These are the spatial cuts I'm making to find the entanglement. But of course, ergodicity or not will depend on how these spins couple to each other. So we will see what difference that makes. We will show some context. So okay, so the entanglement of non-complementary blocks. Non-complementary means that we want entanglement between, say, blocks A and B, and C is a part which is not belonging to either block, which means naturally systems A and B are in a mixed state. They are not in a pure quantum state. They are not in a ket, they are in density matrix. And we cannot use the measure which is very popular, okay, von Neumann entropy. Okay. So one has to use something else, which is called negativity. It is computed in a complicated way, but it works for mixed states. Okay. I should have clarified what we mean by entanglement when we think of mixed states. Okay. It can be quite surprising. Say you take a maximally entangled state like a singlet, up, down, minus, down, up, with half proportion, mix it with another maximally entangled state, say a spin 0 triplet, up, down, plus, down, up. Okay, both are maximally entangled. You throw a coin, half time you give that, half time you give the other one to someone. Because the phase information is completely lost, it's a completely disentangled state. Means someone can exactly reproduce that statistics by generating states locally and calling each other up to correlate their actions. Like you produce up, I produce down. You produce down, I produce up. Okay, but there's no phase relation. Okay, so those are called as separable states which you can synthesize by calling your friend up by a telephone or a classical channel. Right? And states which necessarily require you to transfer a qubit or bring your system and your friend system to interact and go. Okay, that is those are entangled states. Okay, so there is a measure, this negativity, which specifies that, where what you have to do is a complicated procedure. You have to take a density matrix and do its partial transposition. So only the kets and bras of one of the subsystems need to be exchanged. Okay. And the resulting thing, if the system is entangled, then the resulting, when you do this operation, if the thing does not stay a density matrix anymore, which is found out from their eigenvalues becoming negative, then the state must be entangled. You know that remain positive even if you change the bras and kets of another system. And then from that one finds a measure. What one does is adds up these negative eigenvalues, takes their modulus, okay, and that gives you a measure of how entangled the state is, called negativity. So this is what we computed a lot for spin chains to characterize their entanglement. Again, just to highlight what kind of spin chains we have in mind, I've just shown, for example, my collaborator, Charles Smith in Cambridge. So you have many dot arrays, okay? So each quantum dot can have a single electron, okay? And the array of that is like a spin chain, or this in this case is like a spin ladder, okay, but very finite size. What measurements can you do there? If you have two neighboring dots, a measurement one can very easily do is the singlet triplet measurement. Okay, so you have a double well. If you prepare a singlet and you lower one well, because it's singlet, they can come together. Okay, if it's triplet, they cannot come together. Okay, and then you do a charge measurement. If you find charge 2, means the original state was singlet. Okay, so by a charge measurement, you do a spin measurement. Okay? This is the easiest measurement to do to measure spins in quantum dots. Okay? You take a double dot and measure whether the spins were singlet or triplet. Now, using these kinds of measurements, what can you do actually? So what is a singlet triplet measurement? It is a measurement of this exchange operator, sigma dot sigma, because its eigenstates are the singlet and triplet. Okay. Now, what is this sigma dot sigma? The sigma dot sigma actually twice the swap operator minus 1. So the isotropic Heisenberg operator is nothing but something which swaps your spins, okay, swaps your qubits. So essentially measuring this singlet triplet is like measuring the swap operator. And so this is the operator we can measure very easily in quantum dot arrays. So what one can do is to use this in the following way to measure negativity. Okay, so first I'm showing that it's a measurable quantity. Then I will show, you know, what quantities are. Okay. So what you can do is you have to take few replicas of the system. Okay. So I know I'm demanding something hard here, but these are synthesized arrays such as quantum dot arrays. Okay. So you can have exact replicas of Hamiltonians. Okay. So exact copies. And then you, of course, create the same temperature so that you have the same state. All these three. Okay. Then what you do is you measure these swap operators one way for these one of the subsystems, say B, and the other in other reverse order for the other subsystem. Okay? So you measure swap between the first row and the second row corresponding qubits as them being a double dot. Okay, sorry. I don't know why these things happened. Okay, Anyway, and then the similarly, but you do in the reverse time order, okay? Then you can measure some moments of those measurements, okay? And from those moments, we found that machine learning can give you very quickly the amount of entanglement as measured in terms of negativity for those states, okay? So we took a large sample, so we knew that when entanglement measured and actual, so measured and actual, we could plot, and you see falling in the diagonal means you are matching. So we trained using various types of states. Okay? This also like for dynamics, you can also train and match. Okay, so the machine learning does much better than all our analytical approximations. So just with 3 moments, which requires 3 replicas, you can get very well this very many body entanglement measure. Now, if you were to able to measure the entanglement, what would you get? Okay, so if you take a typical critical system in its ground state, okay, so we take any model like Heisenberg model or XY model, but you go to a critical ground state, so you have very long range power law correlations. Okay, so you might naively expect entanglement also to go down as a power law with some coefficient. Okay? But what happens strangely is entanglement also has this exponential fall. Okay, and there's very good reason for it. Entanglement, unlike total correlations, is a very monogamous quantity. Okay? Just think, if you are singlet with someone else, maximally entangled, you cannot at all be singlet with anyone else. Okay, so entanglement monogamy is very strong. So you can, if you share, you become less than half with both. Okay, so so this why what happens is if you take 2 separated blocks and compute their entanglement through this negativity, this complementary set kills it a lot. Right? So you have this exponential decay of the entanglement along with some kind of polynomial decay also. Okay. So this is something we learned, that entanglement far away, if you wanted to extract them for something, yeah, it's not very easy. Okay. Now, say a paradigmatic model where we have a lot of entanglement of one impurity spin with a lot of itinerant electrons around it is called the Kondo, is a Kondo model. Okay, so one spin will be screened by a lot of spins, you know, facing the other way, and that collection will be in a singlet with this spin in the ground state. Okay, a very good model which approximates this Kondo effect is this kind of thing. So you take an open-ended spin chain. Okay, it is because you map the, yeah. So yeah, yeah. Yeah, so no, it is a length, so it should be the other way around. Yeah, Kondo screening length. Okay, so it's yeah, it's a one-to-one correspondence, but yeah, so you have the yeah, it's an energy scale, and that's a length scale. Yeah, they're oppositely related. So so there's a range up to which electrons are correlated, and you can use the spherical symmetry essentially to map this to an open-ended line. So the center, this is the center, and this is the radial direction, loose sense. Okay, and then from keeping universality, you can still actually crank up the ZZ interactions so that they localize. So the universal physics is pretty much the same. Okay. And the Kondo length depends on this coupling J dashed, okay, in this exponential way. Okay, so weaker it becomes longer, the screening cloud. Okay? Now, can you use an entanglement measure to really find this Kondo length out, okay, this screening length? Okay? So we can find that out. So we did that with negativity, but I'm not discussing that here. But suppose you know, optimize this for the cloud to stretch for the entire remaining part of the chain. Okay, this is now not the ideal Kondo cloud defined according to RG, but this is the quantum lookout found out from our method of getting the how many spins are entangled with that. And that also has very similar scaling. So we can reduce this to make the cloud, all the other spins of the chain enter into that particular singlet with this. Okay. Now you can take two such things. So it's like an individual spin has a long arm, which is the entangled thing. Okay. So both spins have these long arms. And then if you suddenly connect them in like a quench dynamics in the middle at some time, just weld that coupling. So you have two dots and their leads. Okay, we haven't done the calculation with two dots and their leads, honestly speaking. But if you have two dots and their leads, and you suddenly connect the leads, finite leads at the other end, after some time, those two dots would grow entanglement. Okay, so they would become entangled. Okay? And these are the entanglement dynamics. This can be used to make an entanglement router. I think since time is, I have kind of spoken for very long, I would probably tell the remaining things in a very, maybe more hand waving and superficial way. So there is this new, well, by now not so new. People have been working on it for like more than 15 years now. Is called many body localization. So it's an open question for even longer whether actually interacting many body systems do localize. Okay? So of course, Anderson found that non-interacting many body systems localize very soon. Okay, slight disorder in 1D, they immediately localize. Okay? However, what was an open thing for very long is whether interactions, okay, can actually delocalize the thing. So essentially interactions with other electrons can provide this energy to go up the gap needed to form resonance with a distant place. Okay, so it was a completely open debate topic. And I think Boris Altshuler first in late 2000s showed that it is possible. But then David Hughes and others shown in the reference here showed that in spin chain models, if you took a Heisenberg spin chain and gave a disorder, quenched random disorder, so this is not varying in time, okay, then you had this kind of transition from an ergodic phase, okay, where you had complete thermalization of the chain due to interactions. So you take any part that will quickly go to a thermal state. Okay, while if the disorder extended a little bit, you will not, and there's a mobility edge. So this is actually going up in energy in the vertical direction. Okay, so this is a localization throughout the spectrum. So this is not a localization in the ground state. This is not a ground state phase transition or thermal state phase transition alone. This is a phase transition of every eigenstate, only that the at which, so critical field by here, I mean the disorder field, the critical disorder becomes more in the middle of the spectrum. So this is what is known, okay? And then you can analyze it, of course, using these kind of entanglement measures. And there was a problem in the field also that people from disordered systems, people knew that a scaling exponent had to be larger than 2, but there was no quantity which was giving that. So what we found is if you use another entanglement-like quantity, which is called the Schmidt gap. So you take an entangled state, you split it into half, you can always write it in terms of a Schmidt decomposition. A left part and the right part, where both are orthogonal and there's a number. And then you can take the difference between the largest two. So it kind of says whether there is one unit of entanglement or not. It's not really an entanglement measure, it's like a yes, no. Whether there's one broad unit of entanglement or not. It will not tell you whether there's more entanglement, more details, it's just 0 or 1 unit, okay? That kind of thing is this Schmidt gap. So when that Schmidt gap calculation for these many body localized systems, you do see that this transition, the Schmidt gap, at that time, our numerics was such that in this published paper, at least, we thought it behaved like like um, order parameter. Okay. We might revise this a bit. So it is possible that it is more like a scaling quantity rather than a order parameter. But anyway, the critical new that we found was this larger value. Okay, this is because we are not looking at the details of the entanglement. So I'll clarify the more problem. So people thought that all results in this many-body localization, most of them are obtained numerically by exact diagonalization. So this is an ideal problem for a quantum computer, okay? Because there's no way to analytically solve this model. It's an eigenspectrum transition, okay? So no symmetric disorder. So people won't just believe that the results you obtain are same as in the thermodynamic limit. And it seems that more larger you go, this critical exponent nu seem to be increasing. Okay? But what we are saying is that very coarse-grained entanglement probably achieves its thermodynamic value earlier. Okay? This is kind of our saying in this context. I will skip these things. Okay? Latest thing we considered is this memory. Okay? This one. Okay. So this Schmidt gap delta, okay, we took its derivative so we want to find that place. So we are taking the d delta dh to see where it's peaking. Yeah. So just to get it more sharply out of the system. Yeah, it's a bad. You see the sizes. You see, 18 is the longest spin chain we do it with. So it's pretty. That is the belief. That is probably I don't know whether, so I have to down speak to my postdoc and collaborator about that, but I think yeah, that I hope they did try that. Yeah, they might have, might not have. But yeah, that would be an obvious thing to check. Yeah. But the controversy in the whole thing is like that this transition, so basically the longer a chain it gets, okay, there's more chance of some disorders finding its close partner, and then many electrons here doing a flip flop with that very fast thing so now there are papers written much more recently say that there is no many-body localization transition. It's just the time scale is increasing. So the field is very kind of controversial here, okay? But what we were showing is that a more coarse-grained, like yes entanglement or no entanglement like quantity gives larger new values, means probably it gets to the thermodynamic behavior earlier than further details. But I don't want to say these with full confidence, because this the field is continuously being thrown open by now this. The last thing we look is that in this, supposedly this many-body localized phase was there as a stable phase where all things were disordered. It should have memory, okay? And how do you quantify this memory? Okay. We want to quantify it in really Shannon sense, like number of bits of information. So what do we do is, so we did something like this. We put in some information in some part, like a bit string. We put in some part, 1, 0, 0, 1, 1, 1, whatever. We have to choose over all bit strings to put in. And then we find out how well that memory is held in that part when the system has non-equilibrium dynamics, closed system non-equilibrium dynamics for a while, okay? If it's in the ergodic phase, very fast that information will go away. You will completely equilibrate with the other parts to get into a thermal state. If it's a many-body localized state, hopefully it will preserve the information. So we want to see how good it is a memory, and memory is a temporal correlation. So we want so there's an exact quantity people compute in quantum information, which is the Holevo, which tells you exactly if you have put in some states in a channel, quantum channel. Here the quantum channel is the time evolution, and you're receiving the information in the same place in the future where you put it. It's a communication, but in time. Okay, so the how much of that information is still lingering here. Okay, but this Holevo quantity optimizes over all measurements you can do in the final block. That is the crucial thing, because you might think you encoded 0110 and just measured in the 01 basis. Okay, that would be Shannon information. Okay, but we want to compute. So some of these things would have gone into entangled states, like a 01 could have evolved to 01 plus 10, and a 010 might have gone to 01 minus 10. So in principle, that information is fully there to distinguish that we are underusing it. So Holevo considers all that into account, and then we computed that, and it's not much of a surprise, but we found that, of course, the information, accessible information, black one, is the Holevo is this one, the brown one. Okay. A lot of people have computed the von Neumann entropy, which is the upper bound on this thing. Okay. And then if you dephase the system, you get classical, mutual information. Okay. And then if you just take, single sites, then you get something which people have measured a lot, which is called the imbalance. Okay, between so imbalance is a bit similar to if you want to measure something like staggered magnetization, how different that is. So we can preserve more information if we look at the full quantum information quantity. That doesn't mean we suggest a way to measure it. That's difficult, but more is retained. And the many-body localized phase does retain information up to huge times, 10 to the power 10 in terms of the couplings of the system. So time-wise, we have gone to a very large limit, but thermodynamically, we have gone again to small system sizes. So if we had a quantum computer with, say, 20 qubits or more, then of course the problem will become this. Because in my classical computer, I can go up to any time without putting any decoherence. But quantum computing, that will be difficult, but the other limit can be made better. Yeah, I think this is enough for today. I think I don't want to go into further details. So I have shown both sides of the thing. The first part was explicitly constructed with finding useful things in mind. But I should tell you there's a limitation of usefulness, of course, because we are using very constrained systems, not all tunable systems. And then there's the reverse, that to characterize different many-body systems using quantum information measures, such as this memory measure or different entanglement. Hopefully, they will help in understanding in some way. Yeah. So with that, I would like to finish my talk today and maybe take questions from people. Mm-hmm. Exactly. Yeah. Yeah. Hmm. Yes. Yeah. Yeah. Yes. 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 So maybe the classical, even classical localized magnetization pockets might, I don't know whether people will say that those are many body localization, but of course magnets are interacting ZZ as well, right? So I think classical aspects of many body localization maybe are not that well studied. again, I'm not an expert, but I think recently people might be studying some of those things. So people develop the quantum much more than the classical. Um, so, um, but yeah, so I think, so there is another thing one has to be careful. Sometimes freezing of things may happen due to so we are trying to, for example, suggest some experiments to our quantum dot array collaborators, and there we face some problems. Sometimes energetically things get locked due to boundary effects and things, like two charges, charge, empty has a different energy than charge, empty charge, because one of them doesn't. So there's a VAB, like a electrostatic energy, which is not there. So sometimes the dynamics is allowed energetically, okay, this, even in a non-disordered system. So we want the disorder-induced localization rather than the, but in some sense, this is also because of one disorder, which is the open edges. But we kind of want that disorder throughout the thing to be important rather than one particular, energetic, we call bound pairs and things can happen. So sometimes we difficult to distinguish those two effects. But yeah, you're right. I have to think a bit more about, look up the literature, basically, a bit more about the classical counterpart of these. Definitely there. And I don't know whether people have done much on that. Interacting classical. Yeah, so people, the most popular lab platform for spin chains have historically been ultra cold atoms in lattices. However, people have not particularly done any of the schemes I showed. Okay, though they have been, I would say, very close to doing this quantum channel. So they have looked at propagation of computations. One lattice. So another, and also they have done the same type of experiments in ion trap quantum simulators, okay, also excitations. So those are places where the quantum communication like thing could very easily have been done, okay. Of course, one would also have to think, one would do it only if there is some good use of it in actually connecting the quantum register. So this is, so the thing is, the completion of these schemes have to be system dependent. That is the problem. So where you will apply it. In quantum dot arrays, recently, some American groups from Rochester, collaborating with some else, I don't know. So they have looked at, they have exactly done some of these spin chain entanglement transfers on Nicole and his group. Some of the earliest physical implementations of my protocols were suggested by people in Josephson junction arrays. Okay, so so other theorists, still theorists. So Saro Fazio and others were immediately people suggested implementations in Josephson junction arrays. Okay, the big problem that whether it is useful, and I think people have done implementations. I think there were some Chinese groups who implemented quantum state transfer also using Josephson junction arrays. But I think the more crucial problem is whether in a Josephson junction array architecture or any other architecture, ion trap or quantum dot arrays, whether it's actually a useful way to connect, then it will become important, okay? Because there is these two important opposite ways of thinking. So people think you need perfect fidelity gates. So fidelity is of paramount importance in quantum. And from perfect fidelity, people always think of off-resonant gates through virtual excitations. Okay? So you have a mediator, it's never excited, but then you're fighting the gap. So you have, it's a second order degenerate perturbation theory. you always have coupling square by the gap. Okay, and the coupling square has to be made much weaker than the gap, and it's a huge time-consuming process. But you have a perfect coherent interaction. Indeed, of course, nature also gives us that. I mean, this is why we have any interaction. This is the Feynman tree-level Feynman diagram, essentially, right? Only that there you have all the modes, and here you have a particular mode. Okay? So it's a coherent interaction. But what I'm telling is not to use the coherent interaction. You really convert the excitation to an excitation of this system, which goes very fast. Okay, you convert back, but of course, it disperses. The field is not very good. But you can do a number of times, and then you purify that entire, and you boost it up by local actions. Okay, so then that that scenario, so it more is in the context of something like measurement-based quantum computing, or partly the gates between different registers will be after setting up a good entanglement. And that for setting up the good entanglement, you do not need really a direct long-range interaction. So in that scenario, one should design a complete scalable scheme using that, maybe how many uses, how many purifications, what is the real resource required, and how well does it compete? Say in a case of ion traps, how well does it compete with shuttling ions or with using many photons? Okay, I think it will scale much better than that. But then how do you join that the kind of a eye of an ion trap with two of the horizons? So yes, it's all very open. Okay, or in Josephson junction arrays, instead of using a microwave bus, if you use a bus of qubits, is that really helpful? So these are the problems I'm interested in now, whether we can really make it useful. And so I think individually it has been realized in many platforms, just as a demonstration. But not all of my schemes. Some of the other schemes may actually be used, probably good in digital quantum computers as a benchmarking. Okay. Doing gates by exchanging fermions and things might be very good as a thing to benchmark. So there are some things on the chat, right? How do I see the chat? Do I?
Am I audible? Hello?
Hello. Hi.
Oh, hi. Okay. So I'm audible, right?
Hi.
Hello?
Yeah.
Okay. So if anyone in the Zoom chat, if you have any questions, please, I request you to please unmute yourselves and ask.
Right. Should I check? Yeah, what is in the chat? So no, it's just beginnings live in YouTube and things. Yeah, so there's not a question in particular. But now there is in one chat. Okay. Right. So chat window. So I think so they are not audible. The people who are logging in.
Yeah, it appears that we are not audible. So yeah, whoever has questions, please type it in the chat window.
Hello, I'm audible?
Yeah.
So just first of all, very nice talk. I have one query that you have shown some machine learning fitting. So may I know what are the, the machine learning, the algorithm you have used for that fitting? You told
so,
that.
This is maybe a very technical question. So you mean in the machine learning thing?
Right.
In these fittings or in this, for
In
example,
general, you told that the ML fitting is much better than other
yeah,
numerical
exactly,
fitting.
this
Yeah,
one,
yes,
right,
yes.
right. Oh, I think I have to confess that those that detail will be known by my students and postdoc, but it would be a least squares kind of fitting. I would think. I really apologize. How they did the fitting.
Okay.
Um,
No, it's okay, no problem. And I have one more thing, this spin chain things, all this, I mean, calculation based on at what temperature?
right. Okay. No, so this I can answer. Okay. So we took random, pure states. Okay. So it's we did not take is as thing related to the thermal state of a substance. Okay. So we just
Okay.
the first training set was we just we have this 14 to 16 qubits. We just tell the quantum computer to generate a complete random state of those. Okay. Since these up to 18 qubits you can handle in a classical computer like laptop or something, so you just generate a random state of those. Okay, and could be entangled, could be anything, and you generate a large number. You of course know them, so you send them into your classical machine learning training algorithm, and you compare the cost function with what you have put in to train. That is one set of states. And the other set of states, much more efficiently inputable, are matrix product states. So these are states which are correlated only very in a rather local way. So they have very area law entanglement. So they have a fixed number of bonds between any two parts of the system. So they can be efficiently represented as a product of the same matrix, repeating again and again. Okay. So those are two types of states we trained with, and then we also after the training we gave the same type of states to them again to check how well they have learned. And then this is the after training matching. Okay, only that what aspect of this, so we didn't put these states directly into the machine. We put measurements on these states on that singlet triplet measurements that I showed into the machine when they're worked through the machine. And for that we required yes, so you see for with machine learning, we got the fit with this picture of 3 copies of the state, as good as what you would get by 10 copies of that state if you wanted to use some polynomials to fit it, like Chebyshev polynomial and things like that. You can also use to fit that entanglement measure. So that is again, I don't know the details of how you fit with the Chebyshev, but essentially the aspect of the measurements that you use are certain moments of this partial transpose of the state, and those moments you measure in this way, exchanging one way or exchanging the other way in the two subsystems, measuring the swap operator between first on the bottom 2, then other 2 for the subsystem A, and first top 2 and then bottom 2 in the other subsystem B. Then we get these moments of partial transpose to the power m. M is the number of replicas, number of copies. So up to the third moment is enough as an input for the machine learning algorithm. While if you use other analytic fitting devices, we require like 10 replicas, moments of the up to the 10th moment.
Okay. Okay. Thanks. And what is the typical coherence time for this spin chain thing?
It will depend on the implementation. So I think in if I'm thinking of quantum dot arrays, then the coherence times are of I would say they are now so they would be like maybe microseconds, 10 microseconds, things like that.
Okay, quite large.
Electronic spins. So essentially it's the coherence time of electronic spins in solids. Okay, So of course, with lots of spin echoes, so if you continuously go on flipping your spins, then you can enhance these things, maybe 100 microseconds at best in solid state environments.
So quite large.
Yeah, so it's not like atomic physics, yeah. But if you do it in optical lattices or ion traps, then internal state coherence is very long. But there are heating and other effects over millisecond time scales, which can feed back perhaps into those. So, yeah, so I think you are safe if you keep your dynamics to be of the range of couplings to be kilohertz, or so you are safe. If dynamics goes below kilohertz, then in atomic systems, one has to think of the coherence. While in solid state systems, you have to keep kind of maybe hundreds of kilohertz dynamics safe.
Are there any other questions on Zoom? Hello, am I audible?
Yeah.
Oh, I see. Okay. Oh, it looks like there are no more questions on Zoom then. So,
okay.
Yeah. Thank you.
Thank you. Thank you. Okay, no, definitely, yeah.